In this lesson, we learn how to do full factorial design for 2 levels and when factors are more than 2. So before that, let me show you the connection between regression and the type of design of experiment and analysis that we did before. So let's say we have y as response and x's are factors that we have. So we have x1, x2, and x1 times x2, which is the interaction. So if x1 and x2 are, let's say, continuous, they could be discrete as well. But before that, let me show you the connection between regression and design of experiments and main effect and interaction effects. Let's say we have a response variable y, and we have 2 factors x1 and x2, and interaction effect, which is x1 times x2. We can define a regression model which relates those factors to response with some coefficients, the linear function, as you can see. So this is the intercept. This is the coefficient for x1 or factor 1, coefficient for factor 2, and the interaction coefficient. So if factor 1 is significant, means the coefficient in the regression should be significant. So it has something to do with the main effect of factor A. As a matter of fact, the connection is defined by this equation. The main effect of factor A divided by 2 gives you the estimated coefficient for beta 1. And the main effect of factor B divided by 2 gives you the estimated coefficient for beta 2, and for interaction is the same thing. How we can get that coefficients? Another way is to just design an X matrix similar to what we did in regression. This is a design matrix that we had. So the very first ones, these are basically for intercept. And this is the design matrix. It means factor A at low level, factor B at low level, A at low, B at high, A high, B low, and both of them high. And this is the last one is the multiplication of these 2 columns. Then we can have X transpose X, and we can find, using the equation that we had with regression, we can find all betas. That's another way to calculate those coefficients. So you can see that the connection between the design of experiment analysis and regression here. In the Minitab also, it gives you the coefficients, and if you have coefficients, you can easily find the main effects, the value of main effects. So what if we have more than 2 factors? Let's just start with 3 factors. In that case, as you can see, the model would be 2 to the power of 3, because we have 3 factors each at 2 levels. So 2 to the power of 3, it gives us 8 treatment combinations. And as you can see, that's this is the design matrix or test matrix. So it's negative, 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 and then positive, negative, negative, and so on and so forth. We have 8 different combinations. And if we have replication, we repeat this test matrix. If the replication is 2, twice. If it is 3, 3 times, and so on and so forth. If you remember, when we have 2 to the power of 2 design, we used a square to show the design. Here, since we have 3 variables, we can use a cube to show that. And basically, when all the variables are at low level, when we have 1, so in this cube, A is this, B is this guy here, and C is the height. So if all of them are negative, we have 1. If A is positive and 2 others are negative, we have A, which is this guy. Here would be B, which is this guy. B is positive, and A and C are negative. This is AB, because A is positive and B positive, which is this guy. Because A is positive, B is also positive. And I can say this is C, this is AC, this is BC, and this is ABC. And we can find or associate each corner of this cube to one of those runs or treatment combinations. Okay, how about calculating the main effects? Again, it's going to be the average at high level of A. Let's say this is A, this is positive, this is negative. So average of these basically points minus the average of these points. Or in other words, we can use contrast and divided by 4 times n. So it's a contrast of A divided by 4 times n. We can have a similar equation for B, as you can see, or C, the main effect of C, which is the contrast of B divided by 4n, or contrast of C divided by 4n. How about interaction effects? Now we have three two-way interaction effects because we have the interaction of AB, we have the interaction of AC, and we have interaction of BC. And again, we can use basically the contrast of AB. Here is the point. There are the points that have positive AB, and here are the points that have negative AB, and we can calculate the main effect of AB here. And we also have a three-way interaction or three-factor interaction effect, which is ABC. So we can define easily an ABC column here, which is the multiplication of all these three columns. For example, this is going to be negative, this is positive, this is positive, negative, positive, negative, negative, and positive. So the average of cases with positive level, high level, minus the average of cases with negative level, this gives us the contrast that we are looking for, and divided by 4n. Here is the summary. So that's the main effects. These are two-way interactions, and this is three-way interactions for 2 to the power of 3 design. Now let's see one example. In this example, we have three factors. We have factor A, which is feed rate in a machining process. We have factor B, depth of cut, and we have factor C, which is tool angle. Okay, and what is the response variable? After doing machining, we measure the surface finish. And as you can see, it's a 2 to the power of 3 factorial design. So we have 8 treatment combinations, and we repeat the experiment twice. So 9 and 7 is for the first factor, and so on and so forth. So as you can see, we have total values here. And this is the cube related to this experimental design with the individual experiments and the average in parentheses. How we can do the analysis? As I said, we can easily use the equations we have. So that's for calculating effect, and that's for basically calculating sum of a square. Let me just go over one example. For example, effect of A is contrast of A divided by, what is n in this case? 2 is n because we have replication 2. 2 to the power of k minus 1. K is the number of factors. In this case is 3 minus 1. So what is contrast of A? It would be, if I go back, that's the contrast of A, which is A plus AB plus AC plus ABC minus B minus C minus BC minus 1 divided by 2 to the power of 4 times 2. So that's how we calculate the effect of A here. And if we do the math, the effect of A would be basically 3.37 in this example. And we can do the same thing for other factors. For SS, we can do SS of A, which is contrast of A. The same thing as square divided by n. Here is 2 to the power of 3. So it's contrast of A squared divided by this number, which is 16. Then based on that, we can find the sum of the squares, degrees of freedom, mean square, and F. And as you can see, the p-values corresponding to F tells us factor A is significant. As you can see, factor B is on the borderline. It's around 0.07. Factor C is not significant. The interaction of AB is not significant. And all other two-way and three-way interactions are not significant. That's basically the way that we can say which factor is important or significant, and how we can find the value which, let's say, maximizes the surface finish. So we can do that using the regression analysis that we have. So here is one example. You can see this is the output of Minitab. Based on the effect, we can get the coefficients of regression. Here are the coefficients, which is each effect divided by 2. Then if I have these coefficients, so I have this equation, I can tell that what is significant is A and B. So none of all other factors are significant. So I can get rid of them and then just focus on A and B and see which levels of A and B is gonna maximize the surface finish. Now let's see when we have k more than 3, or for a general k, how we can calculate the effect of each factor and how we can calculate sum of a square, which is used for constructing ANOVA table and consequently performing hypothesis tests on the importance of each factor. So when k is equal to 4, as you can see, and because we are talking about 2 to the power of k design, which means each factor has 2 levels. So we have a, b as basically -1 and +1. We have factor c and factor d. And as you can see, 2 to the power of 4 means 16 different treatment combination. And this guy here is going to be our treatment, our design matrix. And here are the equations we are going to use for basically finding effect and sum of a square. And for contrast, it's easy because we can find the levels that A, for if we want to calculate contrast of A, we can find the levels for which A is positive and the levels for which A is negative. And then if we subtract them, that's going to be the contrast. Now let's see how we can use Minitab for performing 2 to the power of k design of experiment and analyze the results. Here we have one example. In this example, we want to see what factors would affect the taste of a soft drink. So for that, we selected 4 factors: the type of sweetener, the ratio of syrup to water, the carbonation level, and temperature. And we, for different levels, so all of them are at 2 levels, -1 and +1. And for different treatment combination, we made a soft drink and gave it to some subjects, and they gave us a total score, which is a response variable. So we want to analyze this data using Minitab, but first of all, we entered the data, but first of all, we need to tell Minitab that this data are design of experiment data and what type of design of experiment. So we should define this design matrix to Minitab. For that, we go to a stat menu, design of experiment, factorial, define custom factorial design, and as it says, so what are the factors? Sweetener, C2 syrup to H2O, carbonation, and temperature. And 2-level factorial design, that's what we are using. Low and high, as you can see, all of them we set numeric. We can say they are coded because it's not actual values, and numeric -1, +1. And for the design, we just use the default that we have, and we push OK button. So as you can see, it enters 4 new columns, and this is basically the way that Minitab understand what type of design it's being used. Now for analyzing it, stat DOE factorial, analyze factorial design. What is the response? C5, which is total score. Here terms, as you can see, we have main effects for all factors. We have 2-way interactions, and we have 3-way interactions, and finally we have 4-way interactions. Push OK button, and we push OK here. So this is the significance of each factor. As you can see, it's a Pareto chart. The most important factor is A, and as I said before, if it crosses that threshold, then basically we have a significant factor, otherwise we don't. A factor is here, is significant. 3-way interaction, ABC and ABD are very significant. AB interaction is also significant. D is close, okay, so it's under kind of like borderline. However, other factors are not significant. What happens since ABC and ABD, all of them are significant? It's an interaction, and it's basically 3-way interaction, which includes C and D and B. Although main effects are not significant, we should include those variables in the study because the interaction is significant. Here is an ANOVA table. The p-value columns are here, and you can see which ones are significant. And as I said, factor 1 is significant. The 2-way interaction, 3-way interactions, 2 of them are significant. And factor D is very close to being significant. And if we want, we can have the regression coefficient, regression model, as you can see. And for this regression model, we need to use -1, +1. If it is -1, we just, for example, let's say the low level of sweetener, we just replace sweetener with -1, and then we can do the prediction. Okay, now let's look at the some interaction plots and main effect plots. Again, DOE stat factorial, analyze factorial design, factorial plots. We have response total score, and these are the variables should be selected, and we push OK button. So here is all the interaction factors, that two-way interactions. So as you can see, the two-way interaction between sweetener and syrup is here. The way that we interpret this chart is as follows. So let's say we are focusing on this chart, which is the interaction between syrup to H2O and temperature. The left side is when syrup at low level, and the right side is for the case that syrup at high level, and different colors. So this is the legend for this row of all plots. So when it's red, it's high level of temperature. When it's blue, it's low level of temperature. So if I want to see what combination is this guy, it would be low temperature, low syrup to H2O. And as you can see, those lines are basically sort of parallel, which means the effect of syrup at low level of temperature and high level of temperature are similar. Therefore, two-way interaction for these two variables is not significant. As I said before, the main purpose of a screening design or 2 to the power of k designs is to identify important factors. Let's say we start with 10 factors, and based on the ANOVA table, we define that 2 or 3 of them are significant. Then what would be the next step? The next step would be to have multiple level factorial design like ANOVA. Okay, for example, let's say we have 2 important factors, and what we do, we define more than 2 levels, 3 levels for each factor, and based on that we can do more analysis and find the optimal values. When we have more than 2 levels, another positive thing is if there is a nonlinear relationship between the predictor and response. For example, there is a curvature between response and the factor, we can capture that. With 2 levels we cannot capture, because with 2 levels we can capture only linear relationship. So if I have 2 levels, factor A, this is response, and this is factor A, this is -1, +1. For 2 levels I can only capture linear relationship. I don't know if in between this is something like this or something like that. However, if I have 3 levels for factor A, let's say -1, 0, and +1, and if the values are like this, then I can say, okay, there is a curvature relationship between factor A and response. Okay, and that's why if we want to optimize the response, it would be a better idea to use more than 2 levels, because we can capture the curvature. And but the main reason of using 2 to the power of k designs is to just screen and funnel the factors and remove the insignificant factors. Now let me show you how to use Minitab for optimization. Let's say in this example we have 2 factors. One is metal strength, so it's a machining process. One factor is metal strength and the other one is the speed of machine, and we want to see how they would affect the roughness of the machine part, and we want to minimize that roughness. That's the goal. And as you can see, speed is at 3 levels and metal strength is at 2 levels. So at least we can capture the curvature, if there exists any, in the speed, basically for the speed factor. So what should we do? Start with the stat DOE factorial. We need to define the factorial design first of all. So how? Same thing. What are the factors? Metal is factors and speed is factor. There we have 2 factors. And it's a general full factorial design. It's not 2 level, as you can see. One of them is 3 level, so we select general factorial design, and we push OK. We defined the design matrix. What should we do? We need to analyze it. We go to Analyze Factorial Design. Roughness is the basically variable we are interested, is a response variable. The terms is AB and AB, which is the interaction, and we push OK. So as you can see here, we have metal strength is significant factor, speed is significant, but two-way interaction is not significant. It implies that basically the variation of roughness can be explained very well by speed and metal strength. And we also have a regression coefficient, as you can see here, and this is the regression model for prediction. Now let's see how we can include the curvature. For that, we need to use another design, stat DOE response surface, to capture the curvature. We need to define custom response surface. What are our continuous factors? Both factors are continuous, so I select both of them are continuous. If we happen to have a categorical factors, we select it here. Low and high, we know that low for metal strength is 10, high is 20, speed 15 and 45, and these are uncoded. So what I mean uncoded, these are actual values. We are not using -1, +1. Then what type of design? Again, we use the default and push OK. It's been defined here. What should we do? Next step to analyze it. DOE response surface, and then analyze response surface design. And again, response is roughness. Here, there is a difference here, as you can see, between response surface and regular DOE factorial design. As you can see, we have the second term. So we have AABB, which is basically the quadratic term. So metal strength definitely is at 2 levels, so we cannot calculate AA or the quadratic term for 2 levels, so we can exclude that. For speed, we have 3 levels. We can capture the quadratic term, so we keep that, and we also keep the interaction. So we have main effect or linear effect of A, linear effect of B, quadratic effect of B, which is a speed, and the interaction. Push OK, and OK here. Here are the results. As you can see, so in linear effect, metal is significant, speed is not significant. Previously, it was significant, and the reason is because the quadratic term of a speed now is significant, not linear term. And the interaction, as you can see, it's not significant. Here we also have regression model. So if we want to do some prediction, for example, we know that the low level of metal strength is 10 and high level is 20. For speed, the low level is 15 and high level is 45. If I want to, and the middle level is 30. So if I want to predict the roughness for a value other than those levels, then I can use this regression model. For example, let's say, what if metal strength is 15 and the speed is 20? So I can replace here metal strength with 15, and I can plug in these two numbers to estimate basically roughness. This is how we use regression model. Let's see how we can do the prediction. As I said, what we can do, metal strength, let's say we want to have 15, and for the speed, we want to have 20, and we can push OK button, and as you can see, it gives us the predicted value for roughness and a confidence interval for that, and confidence prediction. Now, what would be the next step? We want to optimize it. So we can use again Minitab to optimize the response, or we can visualize the relationship between response and the factors, for example, using contour plot or surface plot. Let me start with surface plot because it's easier to understand. I use surface plot. So I want to show the relationship between, is a 3D plot actually, which shows the relationship between roughness and two factors that I have. And view model, so basically the model that we are using is quadratic model. Then I push OK button. So as you can see, in z-axis I have roughness, in x and y-axis I have metal strength and speed. And as you can see, it's a quadratic term. If I want to maximize it, that would be the point. If I want to minimize it, either this or this is going to be the point that we are interested in. That shows the relationship. Another tool which is very useful is contour plot. So I select contour plot, then OK. So what it shows, it's basically the map of the 3D surface plot into a 2D plane. In y-axis I have a speed, in x-axis I have metal strength, and different colors shows the different levels of roughness. So if I want to minimize roughness, definitely I would go with basically this lighter green area. So I need to have metal strength around 20 and speed around 40 to 45. So the area with the same colors have the same value more or less. So for example, let's focus on this area, which is the darkest area, or let's say the second area here. All these points here in this darker green area are have roughness between 280 and 300, which means if your roughness is if your metal strength is between 10 and basically 11, let's say, and all these combinations for those points give you the same or similar metal roughness between 280 and 300. We can also find optimal value, optimize the response based on the factors. So response optimizer can help us with that. What do we want to do? The goal is to, let's say, minimize the roughness, or let's say we want to have a target roughness. So the target roughness, let's say we want to be 250. In practice we want to minimize, but just for the sake of argument, let's say we want to have close to a target which is 250. Then we go to setup. As you can see, it's 250. That's the lower and upper bound based on the data that we have. And for the options, so if you have any constraint, you can have it here. For example, you want to constrain on region of metal strength. I don't want to go below 10, I don't want to go above 20, let's say. We can have it here. The model that you are using again is here, basically linear model with a quadratic effect of basically a speed, linear and the interaction. Then we push OK button, and as you can see, that shows the relationship between response and basically your factors. So as you can see, if I want to have, the target is 250, we can achieve this target with what? With if the metal strength is 16.05 and if the speed is 45. So this is the speed, and that's the relationship between the speed and your roughness. And this is basically the relationship between roughness and metal strength. So if I set roughness at this point, and if I set a speed at this point, then roughness is going to be 250. I can play with this as well. As you can see, if I change metal strength, then I can see how basically Y would change. That is being done by the regression model that we saw on the session. You can see if I change it to here, it's going to be 238. Or I can change the speed. So the middle speed actually is giving us a higher roughness. Okay, with that we finish this lesson, and then we continue in the next lesson with control phase. Thank you.